Okay. So thank you for coming to our first meeting this semester. We're really excited to have like a great list of speakers signed up for the semester. And yes, once again, a reminder, there was a typo in the email, but we'll be meeting at this time. That's 12 Eastern, 11 Central, 9 Pacific. Our first speaker for the semester will be John Lentfer from UC Berkeley, and he'll be talking to us about 1-2 bosonic-fermionic coinvariant ring. Before we begin, we have a community statement that I'll be sending into the chat. So these are just like some like reminders that we all want to like keep in our heads while listening and participating in the colloquium. So the first one is we're all learning. Second one is everyone has something to contribute. And the third one is no one has all the answers. So it's just to sort of promote this like collaborative environment that we want to foster in the colloquium. So take a look at that. And I guess we're ready to start. Good job. Take it away.
Great. Well, thank you, Motzkin, for the introduction. And first off, I want to thank the organizers for the invitation to speak here in the colloquium. And yeah, in mind with keeping in line with the community statement, feel free to ask questions. Unfortunately, there won't be time to explain everything due to the time limitations, but just let me know if you have questions while I'm talking. So today I'm going to be telling everyone about what I'm calling the 1-2 bosonic-fermionic coinvariant ring. And I'll definitely be explaining the words in the title if you haven't seen them before. Okay, so the outline for today's talk is I'm going to do some backgrounds. That's going to include just a quick run through of some basics of symmetric function theory. And then we'll also see the classical coinvariant ring and the diagonal coinvariant ring studied by Haiman in the 90s and early 2000s. Then we'll introduce fermionic variables into the picture. And then we'll go through two really important pieces of previous work on superspace coinvariants. So that's this ring with these parameters 1, 1. The fermionic diagonal coinvariants, that's a ring with parameters 0, 2. And then finally, the main focus of the talk will be on this ring that depends on these parameters 1 and 2, which is going to interpolate between those two. And then lastly, I'll briefly discuss the theta conjecture and some recent work of Arachi, Nadeau, and van den Wingard and how that relates to what we did. Okay, so I'm going to fix some notation. So Sn in MathFrak is going to denote the symmetric group. And let's think about polynomials in n variables, x1 through xn. So the symmetric group acts on these polynomials by permuting the variables. And in particular, it's by permuting their indices. And then for all elements of the symmetric group, when they act on a polynomial, it leaves the polynomial invariant, or unchanged, then we'll call that polynomial invariant under the Sn action. So for example, if n equals 3, if we had x1 plus x2 plus x3, that would be invariant. But again, if n equals 3 and we had just x1 plus x2, that would not be invariant because the element 1, 3 acting on that would give you something different. Okay, so the set of all symmetric group invariant polynomials forms a ring called the ring of symmetric functions lambda sub n. So we're going to work with both the finite ring of symmetric functions with a finite number of variables and infinite number of variables. So the subscript n just denotes that there's n variables, and it's graded by the homogeneous degree of the polynomials. And then so one way to define the ring of symmetric functions with an infinite number of variables is to use the monomial symmetric functions. So let lambda be a partition of D. So that means lambda 1 is greater than or equal to lambda 2, which is greater than or equal to lambda 3, etc. And then all the parts, that's lambda 1 plus lambda 2 plus lambda 3 dot 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 sums up to D. We can define the monomial symmetric function by summing over all distinct permutations alpha of lambda. So that's just rearranging the parts. And then this bold x to the alpha just means x1 is raised to alpha 1, x2 is raised to alpha 2, etc. And then so we can define the dth graded component as the span of all the monomial symmetric functions, which are partition of D, and then put all those together gives us the ring of symmetric functions in infinitely many variables. And then there are several well-known bases for the ring of symmetric functions, which we'll be using today. So these include power sum, elementary, and complete homogeneous symmetric functions. So I won't go ahead and read all the details on this slide, but what I'll point out is the definitions I wrote are for when there's infinitely many variables. And if we're going to restrict to a finite number of variables n, then for all of those sums, we're just also going to say that the index or indices used are going to be less than or equal to n. And then if it's infinite, it's unbounded how large they can get. And then the monomial, elementary, and complete homogeneous symmetric functions give a z basis for the ring of symmetric functions, while the power sums need to be a q basis, so they don't form a z basis. And then lastly, the inner product we're using is the Hall inner product, which is defined by if you take the inner product of the monomial and the complete homogeneous symmetric function, that's going to be delta, where that's either 0 or 1, depending on whether lambda and mu are equal to each other. Okay, and then lastly, probably the combinatorialist's favorite basis for the ring of symmetric functions are the Schur functions. And so there's many ways to define these. The combinatorial way is to define them as a generating function over semi-standard Young tableau. So this is not super important if you haven't seen it before, but semi-standard Young tableau are those are the tableau where the fillings are going to be weakly increasing along the rows and strictly increasing down the columns. And then again, the x to the t notation here means x1 raised to the number of occurrences of 1 in the tableau, x2 raised to the number of occurrences of 2 in the tableau, etc. Or if you're in the setting of a finite number of variables, you can use this determinantal formula. So this is the ratio of two determinants. The bottom one is the van der Waals determinant. So you could also write it as a determinant. Okay, and then a very quick overview of some facts from representation theory that we'll be using. So consider any representation of the symmetric group into GLV. So we can think of that as just the general linear group of finite dimensional matrices of any size over C, the complex numbers. And so it's a very nice result that all the irreducible characters of the symmetric group are indexed by the partitions lambda of n. So in representation theory, if you're given a representation, you often want to be able to describe its structure in terms of its irreducible representations, or equivalently, its irreducible characters. So for symmetric group representations, they have this really nice set of irreducible characters. And so the Frobenius characteristic map is an isomorphism between the ring of virtual characters of the symmetric group and the ring of symmetric functions over Z. And I'm not going to say too much more specifically about it, but basically it just sends the character indexed by lambda to the Schur function indexed by lambda. So what is the utility of this? Basically, on one hand, we have SN modules or SN representations. And on the other side, we have symmetric functions. So if we prove things about one side of this isomorphism, we can then conclude information about the other side. So if we're able to determine the Frobenius character of a SN module, so we can classify the module structure of a SN module in terms of a symmetric function. And then small note, so the virtual characters, that just means you could have a positive and negative linear combination of characters. So that's why we're using Z. If you wanted to use Q, you could extend this to like class functions over Q or something more general on the left-hand side of this isomorphism. Okay, and then just a few more pieces of notation. So if you have a graded algebra, so that means it decomposes into a direct sum of homogeneous components with this nice property. Then you can define its Hilbert series. So the Hilbert series we want to think of is kind of like a graded dimension. So when we set Q equals 1 into the Hilbert series, excuse me, we're just summing up the dimension of all the graded components. And here we're going to assume the dimension of each graded component or homogeneous component is finite. But then this Q to the R is keeping track of more information than just dimension because it's keeping track of the dimension in each graded component. And then furthermore, if R is also a graded SN module, then we can study its Frobenius series. So this is, again, looking at and each graded component now is going to be an SN module, so we can find the Frobenius character of that component and then grade all of those components by Q to the R, keeping track of which homogeneous component those characters came from. So here I wrote F and then char, just to be very clear that when we start with the component of the module, first we take the character in the normal sense of representation theory, and then we take the Frobenius characteristic map, which sends that character to a symmetric function. So sometimes, or oftentimes, you'll just see this written together in one piece, but I just wanted to clarify that point. Okay, so we went through a little bit fast an introduction of just some of the basics of symmetric function theory that we're going to be using. So are there any questions before I continue? So the classical coinvariant ring, so here I suggestively put the parameters 1 and 0, which we'll see these parameters coming up a lot throughout the talk, has n variables. So we start with the polynomial ring and n variables, and then we're going to quotient out by this defining ideal, which is generated by all the symmetric group invariants without constant term. So it's really important to have the without constant term exclusion because a constant polynomial is symmetric group invariant, like 1. And if we put 1 in our ideal, then when we quotient out, we would just be left with a trivial group. So that's why that's in there. And then there's many different generating sets we can use, but today I will use a generating set in the power sum basis and in the elementary symmetric function basis. And the Artin basis is a important monomial basis of the classical coinvariant algebra, and it consists of sub-staircase monomials. So when you look at the definition of a sub-staircase monomial, it's basically you have this maximal staircase shape, which in the example you can see, and then within each column you can fill as high as you want. And so so basically each exponent alpha I is less than or equal to I minus 1. And here's an example when n equals 3. And so to see an example of computing the Hilbert series, if we know that the, so assume that we know that the Artin basis is a basis. Now let's see how we can determine the Hilbert series. So this notation for Q analogs is the Q integer n is defined to be 1 plus Q squared plus ... plus Q n minus 1. And we can think of this as like a Q deformation or a generalization of the integer n, where when we plug in Q equals 1, we recover back the integer n. So you notice there's n things being summed together. So when we plug in Q equals 1, that becomes just n. And then similarly, we can define the Q integer n factorial. Okay, so we're claiming that the Hilbert series for this ring is the Q integer n factorial. And so how will we see that? So basically, look at the example here. So in the first column, there's going to be 1 factorial, or basically there's one choice, which happens to also be the Q number, 1, because x1 can only ever be raised to the 0th power. Then when we slide to the next column, there's going to be two choices. We could have x2 to the 0 or x2 to the 1. So when we have x2 to the 0, that would contribute 1 to the Hilbert series. But with x2 to the 1, the x's correspond to a q, so that would be a q. So the second column is contributing a 1 plus q to the Hilbert series. Then in the third column, there's three choices. We could have x3 to the 0, x3 to the 1, or x3 squared. And that would give us 1 plus q squared. And that's the q integer 3. So if you continue that, you could see that this is, in fact, the Hilbert series.
John?
Yeah.
I ask, so according to the rules for this basis, I can never have x1 in my basis. What is the what is a way to understand that, or why does that happen besides just like the rule?
Yeah, so I'll say a tiny bit more about that in a second, but a simple reason that you can see that is if you look at one of these generating sets. So here, this power some symmetric function P1 of x1 through xn, that's going to be just x1 plus x2 plus dot 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 plus xn. So that's in our ideal. So what that means is in ideal, we have a relation x1 equals negative x2 minus dot 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 minus xn. So we'll always be able to eliminate one variable, and traditionally we eliminate x1 in this basis. So yeah, thanks for the question. And so here, I'll just say a little bit more about why the Artin basis is a basis. So if this slide is confusing, we don't need it, later on. So one way to get our defining ideal is to use the elementary symmetric functions E1 through En. And then so this identity so first what I'm writing here is the left-hand side, I'm just expanding this. And then now if I'm reducing this term here, modulo the ideal, well, everything except for the first term has an elementary symmetric function, so they're going to go away when I reduce it modulo the ideal. And so it's going to be just equivalent to 1. Okay. So if I adjoin an intermediate T to our ring, so I'm forming a ring of formal power series, that means I can divide, and so I'm just moving the terms that have a xi to the other side. Okay. Now I'm going to compare coefficients on both sides. And so in particular, I'm going to look at the coefficient of t to the I. So on the left-hand side, there's I minus 1 terms, and each term can contribute at most one copy of t. So there'll never be a t to the I on the left-hand side of this equation. So that's going to be 0. And then on the right-hand side of the equation, if you know the generating function for the complete homogeneous metric functions, you'd conclude that the right-hand side is the ith complete homogeneous metric function, but in a reduced subset of variables. So it's in the variables only from xi up through xn. Okay, and then the next thing that we can do is for this complete homogeneous metric function in a reduced set of variables, you can extract the, like a leading term, the highest power of xi that appears is xi to the I, and then everything else is going to be xi to a lower power, and then some complete homogeneous metric function that doesn't include xi. So basically, whenever we have an appearance of xi to the I, we can actually, or higher, we could reduce this to some linear combination of lower exponents of x to the I. So this shows that the sub-staircase monomials form a spanning set, and you do a little bit more to then conclude that it's a basis. But this was a nice argument first done by Artin. So hopefully that helps provide a little bit more background. And so this shows that it's not too difficult to study the classical coinvariant ring. All the other coinvariant rings that we're going to be talking about are significantly more difficult to prove things about. Okay, so in the 90s, Garcia and Haiman were very interested in studying this diagonal coinvariant ring. So now the difference between the classical and diagonal coinvariant rings is now we've got two sets of n variables. So let's call them x1 through xn and y1 through yn. And then in our defining ideal, this is generated by all polynomials, again, without constant term, which are invariant under the diagonal action of the symmetric group. So the diagonal action of the symmetric group is it just acts by permuting the variables, via their indices. But just notice that it's the symmetric group Sn acting. It's not S2n acting and permuting everything. So it's permuting the x variables in the same way that it permutes the y variables. And a generating set for the defining ideal is given by these polarized power sums. So this is kind of a generalization of the power sums to two sets of variables. So we've got a nice description of that. And there is a symmetric group action on the diagonal coinvariant ring given by permuting the variables. So this is also a Sn module, and it will decompose as a direct sum of irreducible Sn representations. And it's also bigraded both as algebra and as a Sn module. So we can give it a bigrading with one grading for the x degrees, which we'll call q, and one for the y degrees, which will be t. And then so this slide is not essential for what we're going to continue talking about, but it's more of a motivation for why this ring attracted a lot of attention from combinatorialists. So a quick, I'm not going to define the integral form of Macdonald polynomials, but just know that they're a basis for the ring of symmetric functions, but now the coefficients also include two indeterminates q and t. And then define n of mu to be the sum over I, where it goes over all the indices of the parts of mu, I minus 1 mu I. Then you can define an eigenoperator called nabla by nabla of the integral form Macdonald polynomial equals this certain eigenvalue, which is in terms of this mu numerical statistic, times the integral form Macdonald again. So this definition of nabla is not so bad once you unpack it. The difficulty in applying nabla to other symmetric functions like En in the theorem below is that you also have to do a change of basis between the Macdonald polynomials and the other bases that we saw, like the elementary symmetric function. So that adds another layer of complexity into unpacking what nabla of En is. So in the following theorem, which is due to Haiman, he was able to find the Frobenius series, the Hilbert series of the diagonal coinvariant ring, and then consequences of these include the dimension of this ring is n plus 1 to n minus 1, which is the number of parking functions on n cars, and counts a lot of other things in combinatorics rooted forests. Very important number sequence. And then also the sign character, its bigraded multiplicity, is the QT Catalan number. So that's a QT analog of the classical Catalan numbers. When you plug in Q equals T equals 1, you recover them. So what was really interesting about this theorem was parts 2, 3, and 4 all follow from part 1 and seem to be, easier to prove. But at the time that he proved this theorem, which had been open for about 10 years, no proof of any of the other parts was possible independently of first finding the full Frobenius series in part 1. And then the other things were deduced as consequences.
Question. Could you
Sorry, go ahead.
Could you always go from the Frobenius characteristic to the dimension?
Yes, absolutely. So to go from the Frobenius, here I wrote it, you can see from the Frobenius series to the Hilbert series, you take the inner product with h1 to the n, and then to go from the Hilbert series to the dimension, you just plug in for all your indeterminates 1. So Q and T equals 1. And then you'd have to, do some symmetric function combinatorics, but then you would conclude that. And that's exactly how he did it. He showed that these followed from the result in that way.
Okay, yeah, and this is like a general thing that would work for anything, or is the H1n special in this case?
So in general, if you have a Frobenius series, no matter how it's graded, you'll be able to deduce the Hilbert series from it.
Okay, cool.
Okay, so here's like a example of a when n equals 3 for the diagonal coinvariant ring. So I just listed out explicitly, the generating set for its ideal. So you see we've got some power sum symmetric functions in the x variables, some in the y variables, and then we've also got some of those polarized power sums in the x and y variables. So when the polarized power sums didn't actually use both sets, I simplified them to just the regular power sums. So for example, you could use Macaulay 2 or your favorite computer algebra system, and it'll run a Grosvenor basis algorithm, and it will give you out a basis. So of course, each of these are representatives of equivalence classes as well. So, there's different choices for these representatives. And then how do you get the bi-graded Hilbert series from that? So basically, wherever we see a x variable, we're just going to swap that out for a q. And then when we see a y variable, we're going to swap that out for a t, and then we're going to sum everything up. And then to get the Frobenius series, we also have to consider the S3 structure. So we need more information about it than just the monomial basis. So just this basis of 16 elements isn't enough to tell us what the Frobenius series is. So there's some algorithms you can apply to this that basically use some linear algebra and also applying some different Young subgroup partial symmetrization or anti-symmetrization operators to this. And that will allow you to compute the Frobenius series as well. But that's more complicated. So I'm not going to go over that right now. Of course, for this case, you could use the theorem, but I was showing how if you wanted to compute it on your own, how you would do it. And then continuing, so we've got one set of variables, two sets of variables. What about 3 or more? So in 94, Haiman conjectured the dimension of the triagonal coinvariant ring to be this nice formula, and also conjectured this beautiful formula for the sign character. And so some people, including Bergeron, Prevel, Rattel, have worked on the combinatorics of these conjectures. So there's some progress in that respect, but in terms of actually proving this conjecture, it's unproven. And then moving up to 4 sets variables, they stop factoring nicely into small primes. So as Haiman noted, 996 has this large prime 83. So the hope of him, so he was not able to notice just a very simple multiplicative formula. So the progress kind of stayed paused here for a long time. Okay, any questions so far? Okay, so everything we've talked up until now is using normal variables which commute with each other. And so fermionic variables are anticommutative variables, and they came into the picture in 2019 due to Zabrocki. So prior to that, there had been an interesting and important problem in algebraic combinatorics called the delta conjecture due to Haglund, Remmel, and Wilson. And that's a conjectural combinatorial formula for this symmetric function, which I'm not going to go into further. And so Zabrocki said, oh, I conjecture that this certain coinvariant algebra has the Frobenius characteristic if you take its Frobenius characteristic, that's going to give us this sum of things that appear in the delta conjecture. So basically, it's a representation theoretic model for this conjecture. And so the difference between this and other diagonal coinvariant rings that have been studied before is these thetas. So these thetas are fermionic or anticommutative variables. So what that means is if we have theta I times theta j, if we want to switch the order of those two, so two adjacent things in an ordered product, we're going to introduce a negative sign. And as a result, if I equals j, you'll get that theta I squared equals 0. So the behavior of these fermionic variables is vastly different from that of the commutative variables. And so this language of using bosonic to denote commuting and fermionic to denote anticommuting comes from physics, and it's been quite popular recently. I'm not a physicist, so I'm not aware of any other connection to physics beyond the names. And so pushing this further, Francois Bergeron became interested in the idea of, well, we can just have any number of sets of commutative variables and any number of sets of anticommutative variables. So here I wrote a really general definition for the KJ bosonic-fermionic coinvariant ring, where each boldface variable represents a set of n variables. And so even you can do this, I won't talk about anything with infinitely many variables, but he also was interested in when there were infinitely many sets of variables as well. And then so again, as before, the symmetric group is going to act on each set of variables by permuting the indices. So the bosonic variables, so the x's, they commute with all variables, including the fermionic ones. Now, the fermionic variables, they'll anti-commute with all other fermionic variables, even if they come from a different set of fermionic variables. And then I kind of alluded to this already when I was talking about a bi-graded Hilbert series, and I hadn't defined what I meant by bi-graded, but basically in full generality, if we've got our KJ bosonic fermionic coinvariant ring, this will decompose as this does decompose as a direct sum of multi-homogeneous components, where we've got a grading given for each set of variables. And so now we can have a really fine multi-graded Hilbert series by looking at the dimension of each of those multi-graded components. And then similarly, because of that SN action, it has a SN module structure. And so we can define a multi-graded Frobenius series as well by looking at the Frobenius character in each of those multi-homogeneous components. And then in response to a question earlier, I said the last line, which is always you can, from the Frobenius series, you can extract this H1, you can take the inner product with this H1n part and recover the Hilbert series. So the Frobenius series is always a more general concept than the Hilbert series. Yeah. Okay, so now I'm going to talk about the first of the two key ingredients in studying the 1-2 case. So 1 refers to one set of commuting, one set of anti-commuting variables, and the name of this ring is often called superspace convariants. So Sagan and Swanson conjectured, and Rhoades and Wilson ended up proving this nice Hilbert series for this ring, which is in terms of some Q analogs of the Stirling numbers. But the first proof of this by Rhoades and Wilson didn't actually explicitly determine the basis, which I'm going to say next. So this superspace covariant ring has what's called a super-Artin basis. So keep in mind now we have to work with ordered products because we have anticommutative variables. So theta sub capital T is going to denote an ordered product just where the indices are in increasing order. And then for any t that's a subset of 2 through n, we can define an alpha sequence recursively. So the initial condition is that alpha 1 is 0. And then for each subsequent term, we use the following recurrence where this chi takes the value of 1 if the statement inside is true and 0 if it's false. So basically what that means is at each point in defining our alpha sequence, whenever I is not in it, we're going to bump up 1. And when I is in it, we're going to stay flat. We're not going to bump up. And so the super-Artin set is basically very similar to the Artin set, but now that maximal staircase shape is no longer just increasing by 1 every time, like, a normal staircase we'd walk on, but it's now some other shape that's determined by this alpha sequence. And then we're also multiplying by these theta variables. So Sagan and Swanson conjectured, and then this was recently proven by Angarone, Cummins, Carr, Murray, and Rhoades, that this is in fact a basis for the superspace coinvariant ring. Okay, so hopefully this picture will help us. So I repeated the definition of the alpha sequence and for the basis here. And so what you can see here is there's several different maximal staircase shapes, which is kind of the outline, not necessarily shaded in. So the first 6 basis elements, these are all the same as before. Those come from the Artin basis. And those we get when T is the empty set. So when T is the empty set, we're going to start with the initial condition 0, and then we're going to 2 is not in it, so we're going to increase. As the staircase goes up, 3 is not in it, so we're going to increase. And then we're going to take all the sub staircases below that. Then for the next 4 basis elements, for these guys, this is going to correspond to when T is the set 3. And so that means at position 3, we're going to fail to bump up the maximal staircase. So that's why it stays flat at position 3. And then we look at all the different sub staircases below that. Then the next 2, these are when T equals the set 2. So it stays flat at position 2, and then it continues to bump up as normal. And then lastly, for this last one, that would be when T equals 2, 3. And so it stays flat at positions 2 and position 3. So are there any questions on how you construct the super-Artin basis? Okay, so the other important ingredient is the fermionic diagonal coinvariants. So this is a ring where we have 2 sets of anticommutative variables. So here they're denoted with theta and c, and defines the ring similarly as before. So Kim and Rhoades were studying this, and they introduced what they call modified Motzkin paths. And so to define a modified Motzkin path of length n, this is going to have n steps, and the steps we can think of them in z squared, and then each step is going to be one of the following 4. You can have a diagonal up step, so that's what the 1, 1 means. You can have a horizontal step with a decoration theta I, where I is the position, a horizontal step with a decoration xi, or a downwards sloping diagonal step with a decoration theta I xi. And then the further restrictions are the first step must always be an up step, and subsequently the path never can go below the horizontal line, y equals 1. So I'll show an example in 1 second. So from those paths, how do we get the basis? So the weight will just be of a step will just be its decoration, or 1 if there's no decoration. And then the weight of the entire path will be the product of the weights of each step. And so Kim Rhoades proved that this set is a basis, the set of all weights of the modified Motzkin paths of length n. Okay, so now the example that I promised. So these, I wrote all of the 10 modified Motzkin paths of length 3, and then below it, I wrote the corresponding basis element. So the first thing you'll see is all 10, the first step must be an up step. Okay, and then after that, from there, we have several choices. So if we're exactly at y equals 1, we can only go up, or like over here, we could go horizontal, but we can't go down immediately because that would take us below the line y equals 1. So the only example where we can go down, this one, is we've already reached a height of 2, so that when we go down, we still remain at least a height of 1. So that's what that restriction is doing. And then so just looking at the weights, that gives us their basis. So are there any questions on constructing the Kim Rhoades basis? Okay, and so using their basis, they were able to give a combinatorial formula for the Hilbert series of the diagonal fermionic coinvariant ring. And so it's nice because it's indexed over these combinatorial objects, the modified Motzkin paths. And then using this result, they were able to show the dimension is 2n minus 1 choose n, which proved a conjecture of Zavocky. Okay, and at last we can talk about the 1,2 bosonic-fermionic coinvariant ring. So this is just a special case of the general KJ bosonic-fermionic coinvariant ring that we talked about a little while ago. But to be very specific, here is the definition. So the x's are, again, commuting, thetas and x's anticommuting, and the symmetric group is acting as before. So the general concept of our conjectural basis is we're going to be interpolating between the super-Artin basis and the Kim Rhoades modified Motzkin path basis. So like before, we'll let C sub S denote an ordered product in the C variables. And now we're going to define for any T and S a subset of 2 through n. We're going to define a generalized alpha sequence recursively. So the initial condition is 0. And then for every subsequent index, we're going to subtract 1. And then if I is not in T, add 1. And if I is not in S, add 1. And so so Bn 1, 2 is a set. It's not a basis. It's conjectured to be a basis. So it's a set that's defined by we take all of the elements in the Kim Rhoades basis, and then we basically take partial staircase, sub-staircase shapes below them. Okay, so the main conjecture is that this set is a basis for the 1,2 bosonic-fermionic coinvariant ring. And so I verified the conjecture by direct computation in some small examples, and it specializes to these other 2 bases, which are known to actually be bases. Okay, and so here's an example. So I restated the definition at the top. So what different possible combinations of T and S can we use? So here n equals 2. So basically S and T can either be the set of 2 or the empty set. And so T equals 2, S equals 2 is not in the Kim Rhoades basis, so we're not going to use that. So out of the 4 possible combinations, there's only 3 that we'll end up using. So first, when T is the set 2 and S is the empty set, that corresponds to this path from the modified Motzkin path basis. When T is empty set and S is 2, that corresponds to this path. And then when both are the empty set, that corresponds to this path, but now there's two different sub-staircase shapes below that. And now for like a bigger example that hopefully illustrates this a bit better. So you can see how in the first line we've got six different basis elements, and all of these are the sub-staircase shapes below the path that just goes up, up, up. So that would be the specialization of the basis back to the all the way back to the Artin basis. And then now, for example, these four, these all are where we have T equals the set 3, S is the empty set. These ones, this one and this one here, this is where T equals 3 and S equals 3. So that step's going down. And so I won't read all of them for us, but a nice visual way where you can determine the maximal staircase directly from the modified Motzkin path is, let me see if I can annotate this, hopefully. So for each step, can you guys see this color okay? So for each step, what you're going to do is you're going to go to the right endpoint of the step, and then you're going to drop down 1 unit, and then that tells you the maximal height for that column. So for like a more challenging example, here, this step, here's the right endpoint, drop down, so that's the maximal height. This step, that's the right endpoint, drop down, so that's the maximal height. And then for this step, that's the right endpoint, drop down 1, that's the maximal height here. So by doing this directly from the path, you can get this maximal staircase shape, and then we're going to do all of the fillings of that staircase. Okay, now let me erase those. Okay. Okay, so are there any questions on the construction of this?
Just a reminder, the down move in the previous construction had no label, right?
So the down moves do have a label. They are going to have a decoration with both
okay. Sorry,
theta and xi.
Okay.
So you can think of it as like, normally things want to rise like this, and then each time you have a label, it like depresses it more. So if it's got 1 label, it's like this, and if it's 2, it's like that. And if you're curious, it doesn't work. I couldn't figure out a way to work with 3 weights. So it seems to stop with 2. Okay, and so to give a Hilbert series from this basis, of course, you could just index over all elements of the basis, u to the theta degree, v to the xi degree, q to the x degree. But because of the nice sub-staircase structure, we can give a Hilbert series, assuming the main conjecture, over a much smaller indexing set, which is just the modified Motzkin path basis. So that's much smaller than the full proposed basis for the 1-2 ring. Okay, so I guess I'll skip the details for that. And then as evidence in support of the conjecture, we're able to show that the cardinality of the proposed basis is the correct dimension, where correct is in quotes because no one's actually proved that, but Zabrocki conjectured that that's the dimension. And this uses an argument that's very similar to one of Cortel and Nunge on Marc Laguerre histories, where we're just refining by paths would end at a fixed height. So we're just partitioning by the different possible heights that the path can end at. So here, like the first row, they all end at height 3, next row, height 2, etc. Okay, so how can we use this to get a Frobenius series? So each basis or each conjectural basis element is an ordered product. So we could reorder it in the following form up to sign. And then we can extract these exponents, alpha I, beta I, and gamma I. So the alpha i's are going to be some positive integer. The beta I and gamma I will always be either 0 or 1, because if we square a fermionic variable, it will be 0. So our important definition is when an index I is an ascent of B. So we're calling I an ascent of B if beta I increases from when you go from beta I to beta I plus 1, or if they're the same, both 1, and alpha I decreases, like with a a modification depending on gamma I plus 1, or beta I equals beta I plus 1 equals 0, and alpha I increases with a modification with gamma I plus 1. And there I didn't specify greater than, like where equality goes, but you can see it there. And so we say that the ascent set of B is just all the indices from 1 through n minus 1 that are ascents of B. So here's a definition of a fundamental quasi-symmetric function, if you haven't seen it before. So in general, this is not a symmetric function. It's just quasi-symmetric. And this depends on a subset of 1 through n minus 1. So that ascent set that I just defined is exactly what we need here to give a conjectural Frobenius series using the basis. So here I just wrote the grading is just given straight up by the degrees. We're going over all the elements in the basis, and we've got these fundamental quasi-symmetric functions. Okay, and here's an example. So I rewrote the definition of ascent up top, and now let's just do when n equals 2, how do we find the Frobenius series? So below each element, I wrote these three tuples are the alpha I, beta I, gamma I. So it's alpha 1, beta 1, gamma 1, and then alpha 2, beta 2, gamma 2. So that's what these are. So in the first example, we always start by looking at beta I first. Here it goes from 0 to 1. So that's this increasing condition. So that means 1 is in the ascent set. And here, since the ascent set goes from 1 to n minus 1 and n is 2, or the only thing that could be in the ascent set is 1. So it's either empty set or 1. So we're done. In this example, both the beta I and beta I plus 1 are 0, but it satisfies the second condition. So the ascent set is again 1. Here, beta I and beta I plus 1 are both 0, but it does not satisfy the second condition. And then with the last one, again, they're both the beta I and beta I plus 1 for I equals 1 are 0, but it does satisfy the condition. So that's how we determine the ascent sets. And then I just plug in the formula, and we get this expression in terms of the fundamental quasi-symmetric function, which we can convert into Schur functions. And here, because it's a small example, the quasi-symmetric functions are Schur functions. But in general, like this example shows, here, this part is truly quasi-symmetric, not symmetric, and it ends up being combined with another part to give us a Schur function. Okay, and in the last few minutes, I'll just say a tiny bit about the theta conjecture and recent work of Irachi, Nadeau, and Van den Wingard. So D'Addario, Irachi, and Van den Wingard introduced some symmetric function operators called theta operators, denoted by theta sub f, where f is any symmetric function. And they did this in order to extend Zebroki's conjecture on the Frobenius series for the 2-1 ring to the 2-2 case. So here's their conjectural Frobenius series. It specializes to Zebroki's conjecture upon setting v equal to 0. On the other hand, setting t equals to 0 gives a conjectural Frobenius series for Rn 1, 2. So a segmented permutation is a permutation of 1 to n, where between any two letters, you could have a separator, which I denote with a bar. So here we can see an example. And then we'll denote the set of all these by SW 1 to the n. And SW 1 to the n KL is a certain subset where each segmented permutation has k ascents and L descents, where a descent can't cross a bar. And so they introduced a statistic called spinversion on segment permutations and split as well. And so over here on the left-hand side of this proposition, that's the key ingredient of the theta conjecture, specialized at t equals 0. And on the right is their combinatorial expansion in terms of segmented permutations refined with respect to ascents and descents. So to recover the theta conjectures for Frobenius series, just sum up over both sides. So we were able to give a bijection between our basis and their indexing, or our conjectural basis and their indexing set, using a recursive algorithm. I'll skip the details of that. But basically, it matches the theta degree ends up being the number of ascents. The c degree is the number of descents. The x degree is their mean inversion statistic, and the ascent set corresponds to their split. And so this establishes an equality of between our conjectural Hilbert and Frobenius series and those of Arrachino and van Wijngaard. So the main difference between our work and theirs is just an indexing set. It doesn't actually say anything about the ring itself, while ours is a conjectural basis. And so at least in small examples, it tells us more about the ring itself. And I framed our work more in terms of results on this ring. They framed their work in terms of more as symmetric function identities. So by combining them together, our results, which may have been stated as conjectures, can be interpreted as combinatorial formulas for this symmetric function. Okay, I'm going to skip that. And so an application of our conjectural basis model is, so here they found a formula for the sign character. And so using the combinatorics, like getting in and working with the paths and the sub-staircases very explicitly, we were able to generalize that to a formula for the hook characters. So this is for the character for a hook shape. And then to get the full character, you would sum up over u to the k, b to the l for various k and l. But so this is a nice combinatorial expression here. And so in conclusion, here's like a summary of what we talked about today. So proving the conjectural basis as a basis would prove both R or Arrachino van Wijngaard's formula for the Hilbert series. If we proved our basis with some more information, that would also prove both of our Frobenius series, which would imply the Hilbert series. The theta conjecture implies the theta conjecture specialized at t equals 0. And the theta conjecture specialized at t equals 0 is equivalent to both of our conjectural Frobenius series. And I'll just finish by saying I've also studied this in types B and I, and have an observation that in those cases, the dimension is given by the formula 2r to the size of w, but this is not expected to hold for all groups, or all Coxeter groups. Okay, here are the references, and thank you for your attention. I'm happy to answer any questions.
Okay, do we have any questions for John?
Hi, yeah, great talk. Thank you so much. I'm curious, you said that you couldn't find a way to get it to 3 variables, three fermionic variables. Could you say like what you tried that didn't work?
Yeah, absolutely. So let me go back to where I did that. Yeah, so basically you could say, okay, let's have T, S, and like R, and R will correspond to like some anticommutative variables rho. So you could say we should have some, recursive definition for some 3 generalized alpha sequence that will be in terms of some chi functions, chi of I naught in T, I naught in S, I naught in R. And, maybe this is like -1 or -2 or something. And then the problem is this basis really relies upon the Kim Rhoades basis, but Kim Rhoades weren't able to extend their results to 0, 3. So I don't know what the theta t CS row R would be exactly. But then even if I have some computations for small examples where I can, just figure out some basis, the problem then becomes I'm like not exactly sure which kinds of steps to use. Like, should the step go down by 2 if it has 3 weights? Should I have like 3 different kinds of down steps with 2 different weights? So I tried several things and the numerology didn't work out. That's not to say nothing would ever work, but just the most obvious thing that I tried didn't work.
Bless you and thank you.
Thank you.
Any more questions?
Yeah, I have a
If not,
question. Have you tried two, how was it called, bosonic variables, so commutative variables, and one anticommutative?
Yeah, that's a
So,
great question. So for this, there's a conjectural basis for that already due to, I believe it's Sergel and Haglund. I'm not 100% sure off the top of my head, but basically they did a scheduling algorithm. So it basically, in 2018, Carlson and Oblomkov proved a monomial basis for 2-0. So like it took almost 20 years after Haiman's theorem for someone to prove a basis in that case. The scheduling algorithm then takes that a step further by incorporating one set of fermions. So that's a conjecture, but that's been around for a couple years now. So the interest in this, in the case I was doing, was because people are eventually trying to converge on the 2-2 case. And so people were not sure how to push the scheduling further from 2-1 to 2-2. So then people started looking at 1-2 to try and, work from both directions.
okay. And any progress in the 2-2 case then?
I looked at it just a little bit and it seems challenging. So not any progress from me so far, but hopefully we get some progress soon. Just in general, the difficulty of a bosonic variable is much higher than a fermionic variable because the bosonic variables have a much richer structure because the fermionic variables kill themselves when you square them. So they're like, in like a very loose sense, their contribution to the difficulty is like much smaller.
Okay. Yeah, very interesting, the talk. Thank you.
Thank you.
all right. So let's thank the speaker once again. And we'll see you all next week.